Okay. Welcome back, everybody, to discrete mathematics. We continue with estimates, and now we want to estimate factorials. So we can have we can start with n factorial being estimated by n to the n as our upper bound. Do you see how we do this estimate? Just every factor is at most n. Can you give me a slightly better estimate by just being slightly less stupid? Yes? How do you do that? Okay, that's good, yes, but like slash like exponentially much. You slash now a linear factor, right? I want you to slash exponential amount. So let's say we have the first n over 2, which we upper bound by n over 2, and the last n we upper bound by n. So, and that would be n to the n divided by 2 to the n over 2. So we slashed an exponential from n factorial. From that upper bound. Any lower bounds? Now that you saw the upper bound, some trivial lower bounds. Okay, that's very trivial, and a better trivial upper bound. A lower bound. We have n. Anyone going higher than n? Yes. Yes, but that's so. This is the best lower bound I can think of, but it scores high on precision, but low on simplification, right? Because we want to know how does this function behave. So now we have where this first one was very simple but very crude. The second one was very precise but not simple because we don't know how this function behaves yet. So better, yes? 2 to the power of n. How did you do that? Let's do this then. Like, except for the first one, each factor is at least 2. Okay, can you improve that one? Yes. You can do the same thing with the first, maybe do that. Yeah. And so what happens here is that we know now the order of magnitude, right? This thing and this thing, it's kind of the same function up until this division by 2. Of course, there's an exponential gap, but it's like this function has the same form in the upper and the lower bound. Or it gives us a good idea on the size of the function. And it's interesting. So you would think of why would I want to care to estimate n factorial? But so in theoretical computer science, we have almost no explicit lower bounds at all. Like we never know, oh, this algorithm you need at least n squared time. Or maybe we know it for an algorithm, but there could be a better algorithm. And there's one exception. Do you know what exception it is? Only one. and everything else derives from that. Well, okay, there's some esoteric other things, but if you look at the general algorithm, then there's only one exception, which is sorting. So we know sorting takes at least n log n times. So this lower bound is ridiculous. It's just slightly above reading all the input, right? And the reason for that is that there are n factorial many permutations. Whenever you do one step of computation, right, you just do one comparison, at most one comparison. But you need, in order to, information theoretically, to distinguish all of those things, right, 2 to the number of comparisons must be larger than n factorial, because there are n factorial many possibilities in how your numbers are ordered. So that means the number of comparisons, at least the log of this, means we have at least n log n. And this kind of really simple lower bound already tells us. And for most applications, these upper and lower bounds are good enough, but we will prove a few better ones. Okay, so we have another example here. Okay, it's a little bit silly, but so you draw, yeah, and people draw a card. What was I thinking here? From a deck of size n. So how does this work? We have 3 people, each of them draws a card, and I guess, do we put them back? Didn't write whether I put them back. Okay, let's figure out whether we put them back. Yes. Okay. Aha. So if no 2 have the same card, then we have a permutation, right? Because everyone draw a different card, so we have a permutation of n. And there are n factorial many ways to do that. But how many ways are there to draw a card with repetition? Like everyone has n possibilities. N to the n. And this now we can upper bound by 2 to the minus n over 2 using this upper bound. Oh, sorry. I guess yes, using this upper bound, right? We have n to the n divided by this. So we already know now that the probability that 2 people draw the same card is extremely low. It decreases exponentially. Okay, and now, is that clear? Any questions to that? And now we proved much better upper and lower bounds. I guess here the base improves from n divided by 2 to n. And here the base improves by putting this divided by 2 there. And in order to prove this, we need the arithmetic geometric inequality. Arithmetic geometric inequality. And we have a plus b divided by 2. So this is a so-called arithmetic mean. It means, yeah, just the average, right? And that's a geometric mean. Don't ask me why it's called geometric mean. But yeah, instead of adding and dividing, we multiply and take the root. Yes? So I draw what? You draw both like A and B. A and B. Now draw a cross. This height, you mean? Yeah. No, that doesn't make sense. It's lower, no? Because it should be somewhere in the middle between A and B. But there's probably a geometric interpretation. I think A times B is a square. Oh yeah, so I guess if you have A and you have B, then you get a rectangle, and you could ask yourself, you want to have the same area, C, how large need C to be such that these areas are the same, right? And then you get the geometric mean. Okay, so there is a geometric interpretation. And now the proof is actually quite simple. So you just need to know the start. And luckily, I've written down the start, otherwise I would need to think. So this is at least 0 because it's a square number. And then we multiply this out. And then we have A plus B larger or equal to 2 root of AB by just moving this term on the other side. And yeah, and then we have it, right? And it's a useful fact to remember that comes up very often. Now we prove this theorem. And factorial is the same as this product I equals 1 to n. Actually, and we look at n factorial squared of I times n plus 1 minus I. So here, I could always write I, but I match up, if you think about 1 times 2 times 3 times 4 times n with n times n minus 1 times n minus 2 times 1. So I match up those guys to write this product. It's maybe the visualization. And yeah, then I want to use the arithmetic geometric mean, so I have n factorial is the same as this product times the root of I times n plus 1 minus I. Now I can use this AGI, and we get product I equals 1 to n. And now we use the lower bound there as, sorry, not bound. And we just add these things together, I plus n plus 1 minus I divided by 2. And just the same, the I cancels out, n plus 1 divided by 2 to the power of n. That's the upper bound. And now the lower bound. And here this term, sorry, without the square root, is just at least n. And so if I equals 1, then this is just n plus 1. And if I equals 2, then this is larger than n over 2. And so this is 2, so that's true. And so, yeah, it's a little bit difficult to explain. But this is for, so we only need to look, to verify this, we only need to look for I smaller or equal to n over 2. And then this part is always at least n over 2. And this part is always at least 2. And then we get the, we have bounded by 2. So maybe I use a different color. Right, for this range. And otherwise, they swap roles. Once I becomes larger than n over 2, these two swap roles. Okay, if we have this lower bound, then n factorial is this n to the power of n over 2. So we replace this by n, then we have n to a half, and then we have n of those factors. Maybe I write it in 2 steps. Okay. Okay, and now we want to find even better bounds. And for this, we need, as a prerequisite, a little fact. Oh, any question to this proof? So this proof uses analysis, or this fact to prove it uses analysis. So we will not prove it here. So we have this function e to the x, or also I guess x for x. And then we have this function which is 1 plus x. And they touch here at 0. And now you can show that e to the x is convex, and you can see that they touch here, and what you get out of this is 1 plus x is smaller or equal than e to the x. And that's a surprisingly useful inequality. And it's very useful here. And it's useless here. So if you know that the values that you're dealing with are around this area, then try to find the derivative here and use a different inequality. But usually this inequality works out quite nicely. Okay, so here we give an upper and lower bound, and now it's really nice because both the upper and lower bound are kind of simple. They only use functions that we know very well. And secondly, they're very close together. They're only off by a linear factor. So Matuszek gives an upper bound proof by induction. Can we skip the upper bound by induction? Okay, I see silence and one nodding. So this one nodding wins. Very good. So I may make this upper bound using integrals. You can look at Matuszek. Oh yeah, by the way, for the exam questions, I typically ask you for each theorem to be, if you're capable of providing one, how to say this, one proof, that's usually good enough for me. So you don't need to learn all the proofs. So we do proof, I guess, upper bound by using integrals. Okay, so let's look at logarithm. So here, the logarithm is to base e. So let me write this explicitly. So ln, I mean the logarithm to base e. And then ln of n factorial, we know using logarithms laws, ln of 1 plus ln of 2 plus ln of n. And this we can draw. So ln of 0, that was 0, no? E to the 0 is 1, yes. So I guess this just disappears. Then we have ln 1, ln 2, ln times 3. I know this is incorrect in the terms of how fast it grows, but I just want to somehow be able to draw this. So far, so good. So I just draw this as like some bunch of rectangles. And then I look at this function ln of x. And then we see that ln factorial is upper bounded by this integral 1 to n plus 1 of ln x dx. It's basically, I look at the area below this function from here right to n plus 1. And that clearly contains all of these boxes. And then magically we can do this integral. So yeah, so you need to know that how is it? N log n is the undetermined integral, but that you can look up in some analysis book, and then you plug in this upper value and the lower value. And then we can go back to n factorial. So maybe I write exp, because then I don't need to write something in here. No superscript. And then we pull out this ln and the exp. So we get n plus 1, yeah, to the power of n plus 1. And then x to the minus n just goes in the denominator. And then we have exp of n. Okay, this is just some, simple calculations. But unfortunately, it's not exactly the upper bound we were looking for here. Where did I write down this here? Ah, yeah. So it's not yet the upper bound we were looking for. So we do a little trick. We know that n factorial is n minus 1 factorial times n. And then we use the upper bound on n minus 1 factorial. And then we get what we wanted. So this n comes from here. The e comes because here's n minus 1. And the n plus 1 to the n plus 1 becomes n to the n, because we used our statement for this part. And that's the upper bound. So for the lower bound, we don't give a proof. But I would suspect that if you use this function, right, then you get the correct lower bound. And that's something like ln of x minus 1, I guess. Maybe we do the lower bound in the exercises. But the last thing I want to say is that there is a very precise formula, which is called Stirling formula. And that one tells you very precisely the asymptotics. So if you're interested in the asymptotics of n factorial, you get this. And this here means theta plus leading constant is 1. Oh, sorry. And the proof requires more analysis, and we don't do here. And so somehow usually when I do something, then this is for me not really useful, because it only tells me the asymptotics, and I would like to know when they start plugging in. So that's a little bit of a downside of this of this estimate. But it's the most precise estimate we have, which is, yeah, we know exactly the asymptotics here. Oh, sorry. So that's the last chapter for today. We look at some asymptotics for, from estimates for binomial coefficients. Let's take n choose k. Can you give me a trivial upper bound? Yes. Yes, maybe a slightly better upper bound. Very easy formula, yes. So, because you don't see it immediately, let me maybe write this out, right? N factorial is n times n minus 1 times n minus 2 times n minus k plus 1 divided by 1 times 2 times k. And so we can pair up those guys here. And each of them is at most n. And we have k of them. Now the lower bound, kind of the simpler bound, is a little bit more difficult. And yeah, so this comes up a lot in algorithms that you say, I pick all elements of size k, I have to go through them, and then this upper bound is usually good enough to give you asymptotic of the running time of your algorithm. For the case that k is a constant. Because if k is a constant, then the lower bound agrees, right? If k is, for instance, 10, right, then this disappears in the big O notation. Yes. So how do we get this? So we look again at these factors, but we pair them up differently. So let me write them down. 1 times 2 times, sorry, n minus k plus 1 times n minus n minus I times n, and then we have here yeah, and we pair them up like this. And for each of them, n minus I divided by k minus I, we can lower bound them by n over k. I don't want to do this computation because I think it's boring, and you're all capable of doing it yourself. But with this, you get this formula. But we can get a much better estimate. By the way, I think you can get even better estimates if you use Stirling formula, but let's not do this for now. I think that's also the last proof I'm gonna show for today. So we see here that the upper bound, this upper bound is quite close to the lower bound we already had. It's just this e to the k that comes in additionally for the upper bound. So we use the binomial theorem. And it's a little bit a mystery to me on how this gives such a good bound. Okay, so we have this 1 plus x to the n, and this is just all these binomial coefficients with this x here that we proved last time, this binomial theorem. And we make the left-hand side smaller, is that right? Yeah, by just taking only one of them. Clearly, this part became smaller if I remove all the factors, as long as each term is positive. So x, or non-negative, I guess. And then we have this clever choice of x equals k divided by n. And if you don't know why should we take that choice, is because it makes this equality as tight as possible. And you can do some differentiation, you see when it becomes tight as possible. But hindsight, you already did this, you don't, once we already have that, we don't need to compute it again for the verification. And then we have this upper bound n choose k is we get this. And now can we find the upper bound for that thing here? So this is a linear function. You know a good upper bound for linear function? Somehow, yeah. We just use on the top e to the k divided by n, because that's the upper bound that we had before. You remember? And then we have here to the power of n, so these n's cross out. And then we get a n to the k divided by k to the k. And that's the same as e times n divided by k to the k. And that's what we wanted to show. So I have 1 remaining minute in this lecture. So let me 2, depending on which clock I look at. But I just see here the workload is a little bit on the high side, I'd say. So did you already also start to recap the lecture material as well? So who did start recapping the lecture material? Who did not recap the lecture material? So once you start recapping the lecture material, it may get even a little bit higher, right? So you didn't include it in the estimation? You did? Oh, but this should not be an estimate. This should be what you, it should be an estimate of the last week. Okay, never mind. But it's just one, that's why you need to ignore outliers. So I wonder how we should reduce. So would you say is a need to reduce the workload a little bit, or you think it's okay? Who thinks? Okay, I guess there's some people who on the lower spectrum, but not that much really. So making fewer homework questions would help? Yes?
Yeah, I guess because in the tutorials we only do the tutorial exercises.
Yes.
And if you have trouble with the homework, you don't have time to.
Yes, yes, yes. So fewer tutorial assignments.
Yeah, or maybe make the tutorial assignments a bit shorter so that you have also have
That's the same, right? Just that they can be done in a shorter time.
Yeah.
I think the speed of the lecture should be all right, no? Okay, so we don't have to do this. Okay, so we will do fewer tutorial assignments and maybe a little bit less of the homework. Yeah, I mean, the homework assignment was meant to, oh, by the way, so did you guys manage the homework assignment? Did you guys manage the homework assignment? Can you give some indication? Okay, so if you really found it too difficult, maybe now is a good time to drop the course. Or you have to take into account that your workload will be structurally higher. But it's your choice, but I think it's good early on to make this decision, but at least you know. So we will try to reduce a little bit also slightly homework. The problem is it's a little bit like a train, right? We get feedback from you, but we already have the second assignment out, so we can't change, we don't want to change the second assignment. So that's why I try to ask as early as possible. But thanks for the feedback, and have fun at the tutorial, and see you on Wednesday.